So if you followed instructions, you've already completed your work here on the notes page, drawing all electric and magnetic fields. Just a quick note, if you do go on to take some more physics, maybe in college, and you're taking like the freshman level of physics and electricity and magnetism, when you take your exams, there'll usually be a whole lot of students taking it all at the same time, so they can't just do it in the classroom. Usually you would be in a really large lecture hall or gymnasium or auditorium or something like that, with a lot of students taking it all at once. And if you're sort of looking out the corner of your eye, you will know when everyone gets to the magnetism part, because you're going to see all sorts of weird contortions with their hands. They're like trying to bend their wrist in weird ways and all sorts of things. And then off in the corner, you're going to see some poor soul using their left hand. And your heart just goes out to them because, you know, they're not going to do well. Because, of course, we know we use the right hand for the right hand rule. That's the only thing that ever makes sense. But this question did ask you to draw all electric and magnetic fields produced by any of these objects. So let's go ahead and start with electric fields. So one of these objects here is going to produce an electric field. So one of the first things we look at probably is number 6. So what is number 6? It's a positive point charge. Is it a proton? I don't know. Remember, not all positive point charges are protons. Maybe it is, maybe it isn't, but we don't have more information, so it doesn't matter because it's going to create the same electric field regardless of what it actually is. And so what do we always use to test for with an electric field? A positive test charge. So you imagine a positive test charge at all different locations around here, and we know we want to draw what this positive charge does to the other positive test charge. We know it's going to repel, so we're going to draw some arrows that point radially away from our positive source charge, and here I'm going to label it capital E. It's always arbitrary however many lines you drew. So if you drew 8, great. If you drew 4 like I did, fine. If you drew 2, that's not enough. Even 3, I'm not really so sure about that. But, you know, if you drew 16, that's fine. But I'm just drawing 4 just because. You want to label as capital E because on my screen here, I'm always going to use red for electric fields, as I've been doing since we introduced them. I'll be using blue for magnetic fields, but on your paper, if you don't have, you know, colored pencils or pens and like that, you want to be able to know which field you're looking at. Otherwise, it can get very confusing. So make sure you do label it with capital E. So what else creates an electric field? Well, I'm sure number 7 does, because of course it's the same exact thing. It's a point charge. If that's positive, it just happens to be in motion. So it doesn't really change anything about the shape. It's going to have the exact same shape. Field lines radiating outwards. Label it with a capital E. The only difference here is that the charge is in motion, so it sort of takes its field with it, you know, so that you'll notice a change in the field strength if this charge is either coming towards you or away from you. It's not really static. Anything else? Well, number 3, of course, because, you know, what is it? It's a negative point charge. Is it an electron? I don't know. Maybe it is. Maybe it's not. It doesn't matter. What would it do to a positive test charge? It, of course, would attract it, so we draw arrows pointing radially inwards, and we label it capital E. And again, if you drew 8 of these lines, 6 of these lines, 10 of these lines, it doesn't matter. I'm just drawing 4 for simplicity's sake. No particular reason. Okay, is anything else creating an electric field? No. Hopefully you did not draw any other electric fields. If you did draw it, for example, for number 1 or 4, or even 5, those are wires with current. Wires with current don't have an electric field. It's just a continuous flow of protons, but for every one proton that comes in one end, one proton comes out the other end, so there's no net charge to this object. And that's how we know an object creates an electric field, is if it has a net charge. What shows it has a net charge? That would be a positive or negative sign. That's the only way we know an object has an imbalance of charges, so it creates an electric field. Nothing else here creates an electric field. So now we move on to magnetic fields. Let's start with number 2. I think it's pretty obvious, right? It's a bar magnet. It's going to create a magnetic field. So now we go to our rules for magnetic field lines. We know they come out of north poles and go into south poles. If you didn't quite remember that, you want to go back and review that. And so here's what the magnetic field looks like. Field line coming out of the north, coming into the south, and then remember they curl around. This is where I showed the video of the person plotting it with the magnetic compass. If you draw some tighter field lines in here, and again label it with a capital B. But they're always coming out of north into south. They actually do continue, remember, through the body of the magnet itself, but that's, you know, it sort of clutters up the picture if we draw that. I think this is sufficient for drawing its magnetic field. What else creates a magnetic field? Oh yes, of course. Number 1, that's a wire with current. Wires with currents create magnetic fields. So how do we draw its magnetic field? How do we determine its direction? Of course, it's a right-hand rule. Is it the pointing or the grabbing one? This is the grabbing one, right? If we're finding the force on this wire in someone else's magnetic field, that's the pointing one. But that's not what we're doing. We're finding the field produced by this wire. That's the grabbing one. So you can grab it, of course, with your thumb pointing to the bottom of the page, wrap your fingers around, and we should get, if you're drawing it with a curved line, something like this, where if you're in front of the wire, the field line's pointing to the left, behind the wire, the field's pointing to the right. We label it with capital B. Now, I also want to draw this with dots and X's. I think that's a good practice to get into. That's the way you'll see it most often in textbooks and on printed pages. And so here's where you take my advice, where you take your actual pen or pencil and you lean it right up here against your paper, and with your thumb pointing at the bottom of the page, you try to wrap your fingers around. When you do so, you're going to feel your fingers hitting the page. It's a very tactile sensation, and you know if they're hitting the page on the left, that's where the X's are. And then you lift up your pen or pencil a little bit so you can wrap your fingers all the way around underneath, and then you stop over here so your fingers are now poking up out of the page on the right hand side, so you put a dot there. And you don't just want to put one dot and one X, so you want to draw some more of them, clustered near and then spread out farther away, clustered near, spread out farther away, to show that, of course, the farther away you get from the axis of the wire, the weaker the field gets. This, of course, is completely equivalent to drawing the curved line. You just want to draw one or the other, and really I think dots and X's is the more sophisticated way to draw it. Okay, so what else creates a magnetic field? Of course, number 4, it's another wire with current. So again, you're going to angle your thumb down into the right, try to grab that wire, or your imaginary wire. This is rather awkward, but remember my advice, if it's awkward, just turn the paper. You can turn the paper any way you want to make it easier, so you're not going to maybe develop carpal tunnel syndrome in your wrist, and then just make sure you turn it back to right side up so that, before you actually start writing things on it. Okay, so we do it like so. You're going to get a field line that sort of points like this. Above the wire, it's pointing down to the left. Behind the wire, it's pointing up and to the right. But let's do it with dots and X's. So here, you have your thumb pointing this away, and your fingers are going to be hitting the paper on the lower left-hand side. So that's where we're going to put some X's. And then you lift it up, and you curl your fingers all the way underneath. And I hope you're doing this. I hope you're not just looking at photographs of my hand. That's not going to help you. Actually, make sure you're doing this, right? Have the pen or pencil in your hand. Try to grab it. Here you can see your fingers are poking up out of the plane of the paper on the upper right hand side. That's where the dots are. And we labeled, of course, capital B for magnetic field. What else is going to create a magnetic field? Okay, number 5. We've seen pictures like this before. This is a wire. It's just that it's sort of poking up through the paper. And this dot here is showing the direction of the conventional current, which is out of the paper. And so you're going to grab your imaginary wire with your thumb pointing out of the paper, wrap your fingers around. Of course, you're going to draw a circle this way in a counterclockwise direction. That's where your fingers wrap around. And you probably want to draw some more circles, again getting wider and wider with more and more space in between the farther you get from the axis of the wire. What about dots and X's? How would you draw this magnetic field with dots and X's? Well, you can't, right? When you grab this wire and you wrap your fingers around, there's no time, there's no place where your fingers hit the paper or poke up out of the paper. That's the whole point, is that you can't draw it with so. That's why you have to do this so you can feel that happening. In this case, you can't. These magnetic field lines are in the plane of the page. Okay, so is there anything else creating a magnetic field? Yes. Do you see that number 7 creates a magnetic field? Yeah, it does, right? Because it's a charge in motion. It's a tiny charge. It's only one of them, but it's still a tiny, tiny current. If that bothers you, imagine there's a whole bunch of them and they're all moving to the right, like when we first had the idea of getting the magnetic force on a current-carrying wire. Imagine a wire encasing this, and the charge is moving to the right. So grab that imaginary wire. Your thumb's going to point to the right, because that's the direction of conventional current. And you're going to feel your fingers hitting the page below, popping up out of the page above. Here's the magnetic field for this individual positive charge moving to the right. Now, I only put one dot and one X, because it's sort of localized. It's only one charge, so it's a relatively weak field, but also it's localized around that charge, and the charge sort of takes it with it. As the charge moves, you're going to feel this field getting stronger or weaker depending on which way the charge is moving, towards you or away from you. But it definitely does create a field. Will anything else create a magnetic field? Number 3, another charge in motion. Oh, but wait a second, it's a negative charge. So what do we do? Hopefully remember, a negative charge moving to the bottom of the page, that's like a positive charge moving to the top of the page. So imagine a positive charge moving to the top of the page as a conventional current, and grab that imaginary wire with the thumb pointing to the top of the page. Maybe do it near your paper again so you can feel your fingers hitting the page on the right hand side, poking up out of the page on the left hand side. So this is what its magnetic field would look like. And again, I'm just going to draw one dot, one X, because it's localized around this charge. As it moves, it sort of takes its field with it. And again, make sure we are labeling capital B, especially in pictures 3 and 7, because it can be very confusing as to which arrows and which dots and X's refer to which field. How about number 6? Does it create a magnetic field? No, it's the only one that doesn't, because of course it's not in motion, right? It has to be a charged object in motion, a current, to create a magnetic field.